This conference will now be recorded.
Hello everyone and welcome to this webinar. My name is Kristoffer Martinsson and I work as Field Application Engineer at Know-How Solutions. And today I'm going to talk about the benefits of using trace on a Cortex-M device. Some practical things: please remain muted during the entire presentation. And if you have any questions during the presentation, you can type them in the chat and I will answer them at the end. So let's get started. First, a little bit about Know-How Solution. So Know-How Solution, we work with development tools for software development. And we have offices in Denmark, Sweden, and Finland. And we cover the Nordic countries plus the Baltics. And we have different kinds of tools like in different areas like functional safety, code quality and testing, and development tools, and so on. Some of our suppliers you can see on this slide. So today I'm going to talk about or going to use in my demo tools from Lauterbach Development Tools. So during my demo, I will use a solution for Cortex-M. It's called MicroTrace, and it's a combined debug and trace hardware from Lauterbach. And it more or less supports all the different debug and trace features that are available on Cortex-M devices. So it has a 256 megabyte of trace memory, but it also can use trace streaming for streaming to your host during recording and so on. And there's also another alternative that you can see on this picture. It's called a combi probe, which is on the picture down to the right, but it's more or less the same features as a MicroTrace unit. Okay, so during my demo, this is the setup that I have. So I have a MicroTrace unit and I'm debugging an STM32F400 board. So it's a Cortex-M4. But most of the things I will talk about today will be relevant for all Cortex-M devices. So first of all, I thought that I should give you some background to what kind of capabilities there are when it comes to trace in Cortex-M devices. And you can see it by these three blocks that are on the right-hand side of this picture. There is an ETM. ETM stands for Embedded Trace Macro Cell, and that is used for instruction trace. Not all Cortex-M devices have an ETM, but quite many has. And there are other blocks in the CPU, for example, the ITM. ITM stands for Instrumentation Trace Macro Cell, and that is mostly used for like getting your printf output over the trace port, more or less. And you also have something called a DWT, or Data Watch Point and Trace Unit. And it is used for a few different things. For example, it can be used for data tracing, meaning recording the accesses to a variable or to some memory address. But there are also other features like interrupt tracing and profiling traces and so on. And I will come to this in a little bit. And so you have these three blocks that can generate trace data, and it could be output in two different ways. One way is the serial wire output. So that's normally, you have that in a normal debug connector because the serial wire output is on the same pin as one of the JTAG signals. So if you're going to use serial wire output, you need to use serial wire debug. So you have this pin available for serial wire output. The other option for getting your trace out is to use a dedicated trace port. And normally for Cortex-M, the trace port consists of 4 trace data pins and 1 clock pin. So you have 5 extra pins for getting your trace out. The ETM, for using the ETM, the instruction trace, you need to have a dedicated trace port with these 4 trace data pin and a clock. You can't get the ETM data out over a serial wire output. So first, I'm going to talk a little bit about what you can do on the Cortex-M when you have a serial wire output. So as I mentioned, you can use all the features in the ITM and DWT. So here I list the things that you can, the real-time trace that you can get out by using serial wire output. You can get interrupt tracing. That is more or less that you can see when the interrupt occurs and how long it takes for the interrupt handler to run to completion or return, so to say. And you have profiling tracing, which is more or less that the ITM or DWT can output the value of some benchmark counters that are inside of the CPU core. I will come to that in my demo later on. And then you have data trace, and with data trace you can specify a certain variable or memory address that you are interested in, and you can see the accesses, the reads and writes, and the value that is read or written from this address. And then you have another functionality called PC sampling, which is more or less that you can instruct the DWT to output the address that you execute on in a certain interval. For example, once in 128 clock cycle. So that means that you can get an overview and use that, for example, for a little bit of profiling. And the last thing you can do here with serial wire output is a software trace or instrumentation trace. And that is mostly used for printf style debugging, more or less. So I will switch to Trace32 and show you these kinds of features inside of Trace32 and how you can use them. First, I'm going to open up some windows here. I'm going to open the normal trace window in Trace32. And I will just open this window. And as you can see here, on the port size, right now I have configured the system to use serial wire viewer or serial wire output. That's the same name for the same thing, or 2 different names for the same thing. And as you can see here, it's also possible to use a 4-bit trace port. But for the first part here, I'm going to show you what you can do with the serial wire output. And then I will open the ITM window here, because that is used to configure what you would like to have output. So I will start with interrupt tracing. So with interrupt trace, we will see when the interrupt occur and so on. So let's make a small recording. So I'll start execution. And as you can see here in the trace window, the trace buffer starts to fill up. And I will just stop the recording and we can look at the result. And the result is the following. Now we'll open 2 different windows, the trace list and the chart window. And I will zoom in here a little bit. So in the chart window, we see the different interrupt handlers that has executed in the recording that I have done. And we will see when the interrupt happens and how long it takes for the interrupt handle to run. So if I, for example, zoom in here a little bit more, you will see here that here we get a systic, and we can actually measure more or less how long it takes to complete the systic handler. It was 6.4 microsecond in this case. And here a little bit later, we get a SVC handler, and I can do the same for that. Just highlight it and see how long it takes to run completion. And this is more or less the same data that we see in this window, the trace list. Here we see all the interrupts and see the entry and exit of these handlers. And you will actually see the time it takes to execute the interrupt handler. You can also use get more statistical view of the execution of the interrupt handler by using the perf menu and function runtime and show numerical. And here, more or less what you see, a list of all the interrupt handlers to the left. You see them here, and you see, for example, how many times this interrupt has happened and the minimum, max, and average execution time of the interrupt handler. So this was a very, very short description of interrupt tracing, and of course you can use it for verifying timing behavior in your application and so on when it's related to interrupts. So the next part I'm going to talk about is profiling trace. So I will disable the interrupt trace and enable profiling trace instead. And as I mentioned before, profiling trace use some specific benchmark counters inside of the CPU. And I'm going to open a window where we can see these kinds of benchmark counters. So I think in most Cortex-M devices, there are a few counters that count specific types of events. I'm not sure what all of them means because this is very specific for Cortex-M devices. But for example, CPI that counts the number of clock cycles for each instruction that exceeds 1. So if one instruction takes 3 clock cycles to complete, this CPI will increment with 2, and so on. And using that, for example, you can calculate the number of the instruction that is executing every second, the MIPS, and so on. And I'm going to use that as just to show you what it looks like. So I have enabled it, and I can push auto init like that, and I will just start the recording here again, and we will just look at the result. And if you would like to look at in the list, you will just see the values of all of these different types of counters, but it might be more relevant, for example, to look at this MIPS view that shows you the number of instruction that is executing every second. So as you can see here, we are roughly at 105 million instructions here, and here it goes down to roughly 80 million instruction per second. So this was just an example. There are more of these counters here, as you can see. I will not go into details about them. You'll have to read if you're interested in the Cortex-M architecture manual to see what they are. So that was profiling trace. The next thing I'm going to talk about when it comes to serial wire tracing is data trace. So as you can see here in the ITM window, the data trace is already enabled. But when it comes to data trace, you always need to select what you would like to record. So when it comes to data trace, you can select a variable or a memory address. So I'm going to use the ADC converter in my CPU to illustrate this. So here at the bottom here, let's make this window a little bit smaller. Here we have the ADC data register. So this is where you can see what you're reading from the ADC converter. So if I right click on it and select breakpoints and trace data like that. So this is actually not a breakpoint, even if it did look like it. This is just tell the debugger that when we read or write from this address, you're going to generate trace data. So the debugger will configure the DWT, the data watch point and trace unit, to send out this information. So let's make a recording of this. And we run it for a few seconds like that. And we can stop the execution. And here in trace list now we see all the values that we have read from this register, as you can see here. So this is all the values in this list. You can do the same thing by using a variable, and I'm going to show you this also. So if you have a variable, like I have a variable in my code called delay val. So if I right click on it and select breakpoint, trace data, the same thing. And now I will make a small recording one more time. And execute for a few seconds like that and stop the recording. You can open the trace list. It will look exactly the way it looked before, but now we can also, I'm going to show you some other things. For example, or not that one. I was intended to open this window. So you can get like a graph. So you are recording the value of this variable or all reads and writes to it, more or less. And then you can have in this case, you have the time scale, so time 0 and negative time back in time, and you see the value of this variable. So here we get all reads and writes to this variable. So we're not missing anything here. And one important thing when it comes to real-time tracing, and all I'm talking about, is that this does not affect the real-time execution of the CPU. You can also get like a list like this, similar view to the trace list, but here you actually see the value in a more easy way. So in this case, here you see the hexadecimal, but here you also see it in a decimal view, depending on what type the variable is. And as you can see, we see both writes as here and reads here. So with this, of course, you can also verify some timing or maybe detect some bugs if depending on what you're reading from some interface or writing to some interface and so on. So this was data trace. So let's remove these. There is one special use case for using data trace, and that is if you have an RTOS. In my case, I'm using an RTOS called RTX ARM, and as you can see here, I have a number of threads here, one called know-how, idle, ADC, LED, and timer. So we can use data trace to see when the different threads are executing. And how you would do that is that you will tell the debugger or tell the CPU to record all writes to a certain variable. And this variable is normally in the RTOS kernel, and it points to the task structure of each task normally. So depending on the operating system, the variable or the symbol name that should be used is different, but you actually don't need to know it because you can use the function task.config with the parameter magic, and the debugger will return the right symbol or right address for you. So in this case, we're going to record all writes and trace data again, like this. And the debugger used the task config magic and change it, or as you can see here for RTX ARM, the correct variable, you find it here, OS RTX info with an offset of 14. But you don't need to know this. Okay, so let's make a recording again. A few seconds here, like that. And we can look at the recording, and it looks exactly the same. As you can see, we are recording all writes to this variable, and we can see the values that we are writing here. And if you compare it to this window, you will see here, so for example, this D138, that would be, in this case, the ADC thread. So at this point, the RTOS kernel scheduled the ADC thread to execute. But you can look at this in other ways, and you find it in the perf menu, task runtime, show numerical, and for example, also show as timing. So let's have these two windows open. So the chart window here shows you a time scale here again, 0 to the right and my negative time. So we're recorded between 6 and 7 seconds. and we can see when the different threads are executing. So you can zoom in here if you want to see more detail. So if you're interested in how long you were in idle here, for example, you can just highlight it like this and see it was 209 milliseconds. And in the statistics window just below, you more or less see how much time you spend in different tasks or threads. So 72% of the time you have spent in the thread know-how, and very, very little time in ADC and lead thread. They are very, very low. So here you can verify the timing of different threads and so on in your system without really affecting the real-time behavior of the CPU. So that was a little bit short what you can do when it comes to data trace. So let's disable this one or delete this one and go to the next topic when it comes to zero wire tracing, because you also have something called a PC sampler. And I'm going to enable this one. So the PC sampler is that you instruct the DWT that each, in this case, every 128 clock cycle, it will output the address that the CPU is executing on. And if we do this, record a little bit, and this is what it looks like. So you see the address here in the address column, and then you actually see also the symbol, so you can see in what function it is and so on. And you can scroll back in time and to see, but normally this window is not so useful, but you can, for example, look in the chart window and you can zoom in here somewhere and you can get a feeling of how your program executing is running. But notice that you are only sampling once every 128 clock cycle in this case. So there are functions that you will not catch in this chart here when you do it with the PC sampler. I will come later on another alternative with it that is a lot better. But you can also get runtime statistics by using, in this case, I'm going to use a command called trace.statistics.symbol like this, and then you can get a feeling on where you're spending time in your code. So the PC sample can give you an overview where do you spend a lot of time in your code. And as you can see, in my case, I spend a lot of time in some library functions. Seems to be some float functions and so on in a library, but I don't really know where in my code in this case that we are using this library function from. You cannot say that by using the PC sampler, but I will come back to later on how you can do that in another way. But you can get a feeling on where you spend a lot of time and maybe try to optimize that part of your code and so on. So that was PC sampler. And the last thing I'm going to just quickly show you is using the ITM for printf style debugging. And I have prepared another script for this. So I'll run another script. And we should also disable the PC sampler, by the way, so like that. And it's very, very simple. The ITM consists of 32 channels. So I can show them here. There is a control register, and here there are 32 channels here, 31 to 0. And you can use them in your software to output whatever you want. So this is instrumentation. So you can use just a macro to write to any of these channels, and this data will be output. And in my case, I will use it for printf. So if I make a recording right now, and as you can see here, there's a lot of printfs here, but the actual data that is output, you see it in this one. Oh, this was, sorry, let's make a new one. but this is actually the data that is output. So as you can see here, we are writing to some address E000, and that is channel 0, but I'm also writing something else to channel with E004 at the end. That's another channel. So you can use all of these channels to separate your data if you want to. But when it comes to channel 0, I'm using that for printf. So that is what you're seeing here and here, more or less. But you can use it for instrumentation trace. So that is the ITM. Okay, let's switch back to my presentation. And the last part I'm going to talk about is what you can do when you have these 4 trace data pins plus clock. And right now, for serial wire, we can do everything that's come out from the ITM and DWT. But if you have the 4 trace data pins, you can get data out for all of these blocks, also the ETM. So for the trace features, if you're using a 4-bit TPIO trace, by the way, TPIO stands for Trace Port Interface Unit. So it's everything that you can do with serial wire, so like interrupt trace, profiling trace, data trace, PC sampling, and software instrumentation trace. You can do that here as well, but it also adds instruction trace using the ETM. So what you can do with if you have instruction trace? So I'm going to switch back to trace 32 again. So let's close some windows here and run a new script to set it up. Let's arrange the window here a little bit. Just going to show you, as I showed before, now we're using a 4-bit trace port and not serial wire, as you can see here. So that's the difference there. And we have enabled the ETM. So what can you do with it? So let's make a small recording. And trace list now looks like this. Here, more or less, you see all instruction that has executed in your code, and you also actually should see the high-level code, but in this case, we are in a library where I don't have it. So let's search for something here. I'm just going to search for a function here. So as you can see here in trace list, we can see the entry of a function speed trouble and actually exactly how you have executed inside of this function. You can use a filter by using the less and more button to actually see more or less on high level code what has executed. So as you can see here, we are executing in some for loops here, and we're executing over and over here, many times here, for example. But I will select to show some more here, like this. And so what can you do with this data? Just using trace list is kind of difficult because there is a lot of data there, but there are quite many things tools that you can use to analyze this type of data. One thing is actually just using the find command. So for example, if you are interested in how often a certain event occur, then you can use the find all button. So in this case, I'm searching for all entries to the function speed trouble. And we can see how often this function is executed here in the TI back column. So with this, you can verify like timing when it comes to any code in your system, how often does it execute and so on. So that's one thing. You could also you open the chart window. It looks very similar to the PC sampler when I was using the PC sampler, but in this case, you are not missing any functions. Here you see everything. So this is exactly the same window. You can just zoom in anywhere. So for example, if I zoom in here, you can exactly see how the different functions are calling each other. So you can see here that echoes 00 is calling some echoes 01, etc. So you see all the function that is executing to the left, and you can easily measure, for example, how long it took to complete this function. For example, like this, it took 5.36 microseconds. And again, this is real-time trace, so it's generated by the hardware in the CPU, so you're not affecting the real-time capabilities of the CPU. Okay, so this was the chart. And of course, there are other things that you can do, use this information for. For example, if you're interested in actually seeing what is going on here, how is the flow inside of this function here at this point, if I do it like this, then you can activate something called CTS by right-clicking here in trace list and setting the CTS. And if you notice, there's a lot of yellow here. This means that you are in CTS mode and you actually have some step back functions here. So you can step your code backwards and forwards and so on, and see more easily follow the flow as it was when we did the recording of the execution of this function. And you can, for example, go back till like that and step out of this function like that and see where it was called from and so on. So that is the CTS, or sometimes it's called trace-based debugging. One other thing that you can use trace for is very accurate profiling of your application. And you find that in the perf menu and function runtime, and for example, show numerical. So let's let this one come process to completion. And I'm going to configure it, so I'm going to sort it internal ratio like that. Earlier, when we used the PC sampler, we opened a similar view. And in that case, we saw a lot of library functions that I didn't have symbol information for, more or less, or a lot of library functions. And in this case, I see something different. So what this means is that when we do ETM tracing or instruction tracing, when we are in the library functions, we can actually see in which of your function that you are actually calling these libraries. So in this case, it's actually a function called trigo here, as you can see. We spend a lot of time in this trigo function. And we can see the total execution time and the number of times it has been called, and the minimum execution time, the maximum, and the average. And actually, you can see a lot more if we just select some other function here. Let's see. I will sort this one again. So for example, this one, data motion waveform, I'm selecting here. And here we can see the total execution time, but we also see the internal and external. So external in this case is actually subroutines. And internal is when you are inside of the function itself. So the total time is split up in different internal, external, but also there are other columns here. For example, you can see how much time this function was interrupted by interrupts and so on. So here you can easily verify by using the max. For example, if you have some demands on some functionality of your code that it should complete in a certain time, then you can easily verify it by checking the maximum execution time here. If it exceeds the allowed, then you could actually check here, or sorry, like this. You can do list extreme, and then you will actually jump to the call of this function when it had the highest execution time here, and you can analyze it further. Maybe also looking in the chart, etc., for it and see what was going on. You can also do something called duration analysis. when you verify timing. And duration means that you get more or less an histogram of the execution time. So you see the number of time, but this was quite a bad example actually. I will select another one. Let's take this one instead. So this column here shows the different intervals in time, so the execution time in different intervals, and you see the number of times it fits into that execution time inside of that interval. So as you can see, there is one time actually it's above 6.5 microseconds and so on. But so this function, it completes in, most often it completes in less than 2.5 microsecond, but a few times it actually takes a lot longer to execute for some reason. So these are good tools for actually verifying if you have some timing requirements in your project. And there's even more detailed views that you could get to analyze your software when it's come to profiling. You could see the same type of data in a tree structure, in a tree view. Let's let it process here. So then it could look like this. So you actually see, get a very detailed view here. So you see the execution time of this virtual function here, for example, when it was called from here in the call stack, more or less. So you see the virtual function here in different places. So because it's called from different location in the code, and then you can analyze further if you're interested in such a detailed level. Okay, so that was something called function runtime. And the last topic I'm going to talk about when it comes to trace, that is code coverage. So as you might understand, when you have this, when you have all the instruction that has executed in your code, more or less you have all the data required for doing code coverage. And of course, this is normally not done by hand. And maybe you have some automated testing that runs on your target, and then you can use the APIs in Trace32 to control Trace32 from a Python script or something else, or whatever you use as a framework for testing. But you can do it from a script or anything, but I'm going to show you just doing it manually and what you can expect of the result. So how it's working is that you run your test and make your recording, and you most likely have a breakpoint when the test has run to completion. And when you have run it to completion, you take the content of the trace buffer here and you add it to a coverage database. And I'm going to do that manually now. I'm going to push the add button here, and it will add the contents of the trace buffer to a coverage database. And actually this you can do as many times as you want. You can make a new recording and add more data to this coverage database. And then you, for reporting and so on, and looking at the result of code coverage, you might want to change the source metrics, because there are different ways to measure code coverage. There are things like statement coverage, decision coverage, etc. There are different ways to measure it. So I will just check statement coverage here, and then we can just look at result. So here we have all the source files in my project, and we can actually see on each and every file. For example, this one, you can see we have executed 72% of the code inside of this source file, and you can expand it down to function level. And as you can see, we have a few functions that have 100% statement coverage, but some of them are incomplete. For example, this one, Morgot here, this is only 71% statement coverage. And then you can actually double click it and see the source code for it, and you see where it's yellow, there you doesn't have statement coverage. So as you can see here, you have executed until this if statement. So that is fine. You have statement coverage there, but this condition has never been true, so you have never executed a code inside of this if statement in this case. And here, this is a good example if I switch to decision coverage. And as you can see now, actually this line, the first line, the if, now it's also incomplete because that's the difference between statement and decision. So for decision coverage, both conditions, well, this condition must be true or false, and so on. So that's also all the source metrics that you can select. And of course, when you do this in an automatic way, you would like to create a report, and that you can do. I'm not going to show this because it takes some time, but there is a functionality for creating a report that you then can open up in more or less in a web browser. It's normally in an XML format. There are other ways to export this coverage database, but that's the normal way. So that afterwards, when you have run your test, you can have you just use a web browser to check the result. But you can more or less check the same way as I have done here inside of Trace32. So that was all more or less that I wanted to talk about today. So if you have any questions, you can either type them in the chat or you can unmute yourself also and ask them if you want to.
I have one question. On a Cortex-M7 with tightly coupled memory,
Yes.
I think the ETM cannot trace every instruction, right?
Yes, it can.
It can?
Yes. This has nothing to do with the memory bus, more or less. The ETM should be connected inside of the CPU core, so it should be able to trace everything that's executing, no matter what memory it executes from.
Okay, but the CPU is running in this case at 600 megahertz.
Yes, that's fine.
And the ETM is only
okay. Okay, for Cortex, normally for all other Cortex devices except Cortex-M7, the trace clock is normally half of the CPU clock. It's hard coded that way, so it's not possible to change. But for the Cortex-M7, since there are M7s that runs up to 800 megahertz, maybe even more, I'm not sure. And then it's very difficult to have a trace clock of half of, for example, 800 megahertz. So the trace clock should be 400 megahertz. So that's normally not possible. But then there are functionality, so you can divide the clock, so you can get, for example, a 200 megahertz trace clock or something like that, and that will work. And the tools from Lauterbach, the microtrace, it supports a trace clock go up to 200 megahertz, and there are no Cortex-M devices on the market that can use a higher trace clock than that, what I'm aware of. And even if you have that, it's not, even if you lower the trace clock a little bit, it's not the problem to record all the instruction that has executed. So it should work anyway.
Okay, I need to try that. Thanks.
Are there any other questions? Okay, if there are no other questions. Okay, there was one more question here from Linus. Let's see if the question comes here. Okay, the question is that I guess this can produce quite a lot of data. Have you ever had any problem with the tracer not being able to log everything fast enough? to the computer, that is. Okay. Yes, it produces a lot of data. The amount of data that you generate depends on how your code executes, or how your program executes. And inside of the microtrace, there is a 256 megabyte trace buffer. Normally, the trace interface between the CPU and the microtrace units is fast enough to capture everything that is executing. But if you would like to record for a long period of time, the 256 megabytes of trace memory that is in the microtrace might not be enough. And then you would use a streaming trace to your PC during execution. And the interface to your PC is a USB 3 or super speed interface. So it can cover reach like something 4.5 gigabit per second. And that should normally be enough to record longer periods of time. But the limitation might also be the SSD drive or the hard drive in your PC. That could also be a problem, of course. But so if you would like to record longer than what you can do with 256 megabyte of trace buffer, then it could happen that the interface between the debugger tool and the PC is not fast enough to cope with it. But normally it works also on quite high speeds, I would say. Okay, so if there are no more questions, then we will finish this meeting. So thank you everyone for joining. This presentation has been recorded, so if you want to have a look at it afterwards, you can just check the recording that you will get a link to in a mail today or tomorrow. Okay, thank you very much for joining everyone.